What we're going to focus on now, and I think in terms of really, getting a good understanding of the world around us, the interesting chemistry, is the top few rows. And the top few rows behave in a certain way. The way we're going to kind of fill in electrons and understand their electronic properties is in terms of the octet. And so there are 2 electrons in this s orbital, and then there are 2 electrons in each one of these p orbitals. So there's 4 total electrons. And what if you remember before, we called these the valence orbitals, the outermost orbitals. And when you fill those orbitals, something interesting is going to happen, which we're going to talk about in a little bit. But we're going to call the 8 electrons in these outer orbitals the octet. And filling these things, and if we fill up all these things, sometimes that can be called filling the octet. And so this idea of the octet is important for understanding why elements behave the way they do, why bonding occurs in the way it occurs, and so on. Okay? And so this word octet is something that comes up a lot when you talk about bonding. It wants to settle at wherever the lowest potential energy available to it is, right? And so we have a much more complicated system here, right? We have much more complicated forces, and we have something that doesn't occupy an individual point in space. So I realize this analogy is not great, but nonetheless, what we have is something similar to that ball finding the minimum potential energy point. We have an electron finding, or electrons finding minimum potential energy points.
The place they like.
Yeah. And so those correspond to these different things, and that's why these different orbitals come about.
That's why we don't go this in depth and
This is
delicious.
so this is far too in depth, but the thing that's useful about this is motivating the octet, I think. You want to tell kids where the periodic table comes from, and you want to tell them why this number 8 electrons is important. I'm not sure the best way to do that. Maybe showing these diagrams is not a good idea. I'm not going to argue with that. But there is something important, there's something physically real that's going on that you can't translate to the Bohr model. And so somehow introducing this, I think, is a useful thing as kids move up and learn more chemistry.
Actually, I don't think. I think the younger they are actually can grasp more, and if you hook onto the Bohr, just showing them this younger,
Yeah.
and then going on, because then you don't have something to go back to like that. My 2 cents.
What's next? So, the way these things fill is in a certain way. We're not going to talk about this so much.
Oh, he just hacked that because we were okay.
Yeah. So the way these electrons fill in is they fill these orbitals in certain ways. And so for helium, say, or for hydrogen, we have 1 electron. So there's going to be, in that 1s orbital, in the first orbital, there's going to be 1 electron there. So this top row here corresponds to 1s, and there's 1 electron in the helium one, in a ground state helium atom. And hydrogen. Sorry, I was misspoke. And the hydrogen atom. In the helium atom, there are 2 electrons. So again, we have that 1s orbital, and we can put 2 electrons into an orbital. So we fill that orbital, and this is a filled valence shell. So then we can move down to the next row, and we can go through the same process, where now the s orbitals over here. So lithium and I think that's beryllium, right? Yeah, beryllium would be putting electrons into that 2s orbital, since we're in the second row. And then we have all these p orbitals that show up. And so if we just jump kind of to the end of the story, we go to fluorine here. We have the 1s, some of the core electrons that are filled in. And then we have the 2s that's filled in. So those are the electrons that come about over here. And then we have 1, 2, 3, 4, 5. So it's in the 5th row or column over here. So we have 5 orbitals to put in the outside. So I've indicated that we have these different orbitals, but that's not so important. What's important is that we have 5 electrons in the 2p orbitals. Okay. I'm waiting for the objections. I don't want to go too fast.
But that doesn't total 8.
No, it does not total 8.
And there's 2 to balance.
Which means that we need 1 more, right? Because it has
5 plus 2. Oh, so yes.
yeah. So it has 7. So this is going to give rise to kind of the characteristic fluorine chemistry.
So it's going to go looking for that last electron.
Exactly. And so another thing, a shorthand that we can do is, you'll notice this 1s is the same as helium. So oftentimes what we'll do is replace the core electrons that aren't involved in anything interesting with just the name of that previous noble gas. And so we could jump down to the next row for sulfur. We could replace those core electrons with neon here. And then we could show what its valence electrons look like. So it has the 3s2, because we're in the third row, sorry. And then we have 4 electrons in these p orbitals. Since you have 3p4.
Is that a standard way of moving or writing out?
What I've done here?
Yeah,
Yes.
that's a standard way of doing that too.
Yeah. So you guys want to take a try at one of these yourself? So how would we do boron?
Where's boron? Where's boron?
Where is it?
The boron is right here. So it's in the second, our neutral atoms, right?
Okay.
But we could talk about ions in the same way. So we could talk about fluorine minus. So what do you think that corresponds to? Fluorine with a negative charge.
It has one less electron, so
One
no,
less
one
elec-
more electron because it's
Exactly.
got a negative charge.
So if we want to talk about fluorine minus, and we want to do this exact same kind of electronic configuration thing with it, what would we do then? We know it has one more electron.
You add one.
You just add one to it, exactly. And so then, coming over here, so what's our noble gas core for fluorine? Fluorine is the second row right here.
Oh, number 9?
Yeah.
So it's helium.
So helium.
So we have helium, which is 2, and then,
7. 2s2.
yeah, 2 is 2. We're filling in 2 P's. The neutral one would have 5. We're going to add one more, so it's going to be 6.
Well, why is that not?
So electronically, this is the same as neutral. So this now has a filled octet. And actually fluorine minus, or this is oftentimes called fluoride, which is what's put in toothpaste, and it's an important mineral or ion for us surviving. This is a very common form of fluorine. It's much more common, I think, than neutral fluorine. And so we're starting to get a little taste of what the octet actually means for the way these atoms behave.
I remember what these neon is for protons.
Yeah. So this is electronically similar to neon, but it still has one less proton, so this is still fluorine.
Good question.
Yeah.
For what is?
Just reiterating this point. So noble gases, there's obviously something special about them. They're not reactors. They, for some reason, occupy that last row of the periodic table. For some reason, and we know that this is because the way the orbitals work out, when you get you get a certain number of electrons, you fill the valence orbitals, and that imparts special stability to those atoms. They don't react with other things. And so we can notice, like with fluorine, it likes to be fluoride. And I probably shouldn't use the language likes, because we know more fundamentally, it likes to have its orbitals filled. And so when we do that, it becomes similar to neon. And so electrons like to fill, or atoms want to fill their octets. And so electronic configurations that look like the electronic configurations in noble gases are very stable, and typically that's what atoms you're going to see them like. Okay? And so, making that point, again, they're going to ionize in ways to be electronically similar to noble gases. And so I talked about a case here where fluorine took on an extra electron to become like neon. But we could also go the other way, right? We could take, which one did we do? What was the top one? Was that? This is magnesium. So magnesium works just fine. So what do you think magnesium would do in order to become similar to a noble gas? Electronically similar to a noble gas. So it's on the other side of the periodic table. It's got all those p orbitals that are empty, and it's got a few electrons.
We could give one away.
You can give one away, yeah. And so then
Whatever's
what
the
would happen?
closest path being.
Then we'd have one here. So this would be magnesium plus 1. So we're still not like a noble gas, right? What else could we do? We could do the same thing again, right?
Yeah, yeah.
So we can
like
take
give
off
enough
one more.
electrons away.
So now we have 0 electrons in this. We have still the core electrons, so it's like neon. So we have magnesium 2+. And this is probably the most common way magnesium is found in nature. So just like how fluorine is commonly seen in this -1 state, magnesium is often seen in this +2 state.
Because it just goes to the noble gas that's closest to it, like is it?
Yeah, it goes to the electronic structure.
Yeah,
like
right,
that,
yeah,
yeah.
yeah. Okay, so it's equally, I don't know, like it's not easier to gain all those electrons or the other ways it's easier? Or
I'm not really
higher
sure if it's
tendency of
easier.
happening, you know what I mean?
It depends where you are in the periodic table.
Tends toward the
If you're-
electronic structure of the noble gas.
Yeah,
closest to
so it'll tend to the noble gas that it's closest to. So if you're on the left side of the periodic table, it's going to tend to want to give up electrons. If you're on the right side, it's going to tend to want to gain them. Yeah.
So in
We're
order.
going to talk a little bit more about that and actually quantify it with something called electronegativity.